Hello, hello, and welcome. Physics C, electromagnetic, class 3, talking about conductors and insulators. I'm going to talk about insulators first, so it's more like insulators and conductors. We'll get through it. So, the idea here is some things conduct electrons, allows electrons to pass through them, and some things don't. So we have insulators, which are pretty, straightforward in life. The idea here is you have a lump of something, and you have charges. These are going to be negative charges. And you have a electric field. So let's say electric field going this way. So when we talk about electric fields, especially uniform ones, I like to draw parallel plates just so we have a more visual way of understanding what the electric field means. So we have a lump, an insulator lump, an electric field going from left to right here. And we have a bunch of charges in it. So what's going to happen then is we have these, we're going to have, no, that's the wrong direction, completely wrong direction. Negative charge goes towards the positive. Towards the positive, away from the negative, i.e. away from the electric field. But since it's an insulator, the charges are stuck within the object. These charges are not drawn to scale. There are many more charges in there. You're probably going to have, yes, you have many charges. Many. So you're talking about multiple charges per atom, because you generally have the same number of electrons as you do protons. So if you have 6 times 10 to the 23rd atoms, you have so many electrons per atom, many charges. Let's not get too carried away. So we have a force, which we have the electric force, F equals QE plus QV cross B. We haven't discussed magnetic fields yet, but we're going to assume that this is 0 for this. We have an electric field, and so we're going to have a pole towards the positive side, away from the electric field, if we have negative charges, net negative charge on this object. But since the charges are, for the most part, stuck here, unable to move, that force is going to be translated to the object, and the charges themselves are stationary. They will not be able to move within the object, they will not jump outside of the object, they stay right there. But in the grand scheme of lives, everything is kind of on a spectrum. There will be some charges moving, more or less. And if you put a great enough electric field, you can always get charges to flow. But generally, before you get any appreciable amount of charges moving back and forth, you're going to break whatever object you have. One common example of this is called dielectric breakdown. So basically, we haven't talked about capacitors yet. We have a capacitor, you have conductive plate, and you have some insulator in between. And that insulator in between is a dielectric. And it prevents the charges from flowing from one charged plate to the other. And if you get a high enough electric field or voltage across them, then you're going to have dielectric breakdown. Basically, you just rip the dielectric to shreds. One more common example of this would be sort of lightning. So you have clouds that are really charged. You have the ground, which is considered a ground, I guess, but you could also say you have a difference in charges between the clouds and the ground, and creates an electric field, and eventually there's an dielectric breakdown, and the charges jump from the clouds to the ground, i.e. lightning. So insulator idea is they are perfectly stuck in place, at least we're assuming for this class, for the AP exam, and the charges don't move within the solid. The solid can still feel a force on it, and so generally the force that's attributed into the charges will then be transferred over to the object as a whole. And we're assuming perfect for this exam. Seem pretty reasonable? Any questions? Okay. So that is an insulator. Now this is put in contrast to conductors. Oop. There we go. Delete and delete. So, I could use an actual circle. Yes. Yes, please. Make bigger. Yeah, I'm good with that. All right. So we have ourselves now a conductor. Also use negative charges. And the idea here then is we have a whole bunch of charges on a conductor and they're free to move. The way this comes about is, let's look at an example. So zooming into the atomic scale, we could have lithium as a good example. So let's say we have lithium, which I think it's number 3, so I have 3 protons. And I think it's lithium 7 is the most common, so it means it has 3 protons and 4 neutrons. And then we'll have some electrons associated with it, specifically 3. So you probably remember from your chemistry class that you have various orbitals. You'll have a 1s orbital. Think of s as the sphere. So I have 1s and then the 2s orbital. And if you have some sort of electric field or give energy, we'll say give energy to one of the electrons, it'll go up an orbital. Up orbitals, possibly plural, maybe not. And if you give it enough energy, it completely gets ejected off. Well, we could draw the energy required, the ionization energy, as maybe this. So this would be 0 for the amount of 0 energy added. And then maybe this would be like the amount of energy required. This will be the amount of energy that the electron has with respect to infinity. Idea here is if you give enough energy to this electron to get it up to 0, then it's free off and it can do whatever, live its little electron life elsewhere away from the atom. So this might be the amount of energy required to take the first electron. Then we'll have like a second, and then maybe a third. Not drawn to scale. So for like lithium, I imagine, this is a bit of energy, this is a lot of energy, and this is lot times more energy. So you could look at it as the first, second, and third ionization. Ionization as in removing an electron in this case. So this could be the idea of removing an electron. The electrons, the charge carrier thingy-majiggers that have to do with conductors, they come from atoms and the electrons move around. So your question might be, why do we have these basically free-flowing electrons? Well, when you have discrete energy levels for atoms, but when you get a whole bunch of atoms in a crystalline lattice structure, their orbitals tend to overlap, and they can't have, when you have overlapping orbitals, you can't have electrons with the exact same energy level. That's why you have orbitals to start with, but now we have multiple identical atoms with overlapping orbitals between them. So what happens is you then get a whole bunch of other orbitals with other energy levels, and this applies to the second and third as well. I'm just doing it for one of them. And I drew 4 here, but really you're talking about, massive numbers, 10 to the 20, 10 to the 30, and maybe probably not 10 to the 30, but 10 to the 20s or so numbers of orbitals, and there's a small difference between them. And so you get so many of these that are close together, they become almost continuous, more or less continuous approximation. And you get enough of them so that it overlaps the 0 energy point, and so you get this band. Now, it doesn't overlap for all materials. This is specifically for metals. So this is, I believe, called the Fermi level. The idea is you have amount of energy for any given atom or any given electron, it's just as easy for it to go as for it to stay with the atom. And so it's really easy to take atoms, push them off, or put them on. And so what happens then is you have all these various atoms together, and they all kind of have these one electron that kind of sort of will go or not go. And you have this band which will provide electrons to the, I guess, entire crystalline lattice structure, solid as a whole. And this is where you get the term sea of electrons, where you have all these free electrons. So you're talking about this top electron level, when it's easiest to take off. You can get a whole bunch of them from the various atoms, and they can contribute to these charge carriers that move or come back. And that's how you get these atoms that are free to stay or free to go. I think it's called band theory. So the idea here then is that explains how you get three of them, but here you see I have extras. Basically I have extra atoms, extra electrons thrown on, which exists, but it's not the normal case. So what you normally see with conductors then, where this normally applies, is let's say we have a square, like so, and this will be, let's do orange, so it looks copperish. So the idea here then is blue, blue. If we hook up a battery like so, it would be pushing negative charges, electrons, this way, and then you're basically putting on electrons here, and it's pushing electrons off here. And since this is like creating sort of like a pressure, I'm a big fan of the hydraulic analogy. I know it's not perfect, but it's really intuitive, and it gives you good enough answers in a quick time. We'll talk about that more when I get to circuits. So the idea is you're creating a pressure almost of electrons here, and they're able to easily flow off this side because of this band theory, where you have these electrons that are kind of ambivalent if they stay with a specific atom. And this pushing, though, would not work with an insulator because they're stuck. So you have this pressure, but you have you don't have an easy flow. And then specifically with insulators, you still have this. You can still have a band theory and band structure, but the energy levels of the atoms, the band doesn't cover the Fermi level, the 0 point. So if we took these bands here and moved them down, you could see that it would take a lot of energy for an individual electron to jump up to that 0 level and then fly off to wherever it goes. So that's the idea of conductors. So now there are a few, not caveats, but implications for this. So one implication is, so I drew a conductor like this with just free-flowing electrons. Let's say instead of this being 3D, this is actually just 2D for this example, which I guess we could have a plate. Nah, we're just going to say 2D. It's like a slice. So you would not, we'll kind of go with it. You would not normally see electrons ranged like this. Additional extra superfluous charges like this. What you would see them at the edge. And the reason for that is they want to try to minimize their energy between them. They want to get as far away from each other as possible. And the way that works the best is to have the charges at the outside. So this would be more of what you would see. Now if it was a sphere, this would be like the center disk of the sphere. It'd still be, you understand. So charges go to the outside. Another implication of this is that the electric field inside a conductor is always 0. So let's look at this as an example here. So we have all these these charges, and we have, let's say, an electric field. Let's get rid of our lithium. Oh, square. Ooh, rounded square. There we go. Nope, want to go back to no color. Yep. These will be the plates for a capacitor. Make them charge is purple. So this will be plus, 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 and plus. And over the other side, we'll have negatives. Negative, 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 and negative. So we have an electric field. Electric field goes this direction because positives are sources, negatives are sinks. They go this way. Now I said that the electric field within a conductor is always 0. It doesn't mean that the electric field doesn't exist. The net electric field is always 0. So what's going to happen then is the charges, let's say this is, this will probably be easier if I make this neutral. So I will salvage my circle over here, my conductor, delete, and then move back. So if this is a conductor, what would happen then is the charges within would rearrange themselves to create a electric field that would counteract the external electric field. So we'd have something like this. Now, even if there does have a net charge to them, they just rearrange themselves in a less obvious symmetrical method. So the idea here is there's now an electric field going this way, and the positive charges to the negative, and this is overlapping with the other electric field going this way. And so as a result, the total electric field within, net in a conductor always equals 0. Another point that it's kind of hard to see from my drawing is that when the electric field lines intersect, then they're always going to intersect at right angles with a conductor. And that's true with charges too. When electric field lines interact with a charged object, it's going to be at right angles. Charge again. Yep. And I think that is most of the knowledge we need for this. Another question you might have is, where do the positive charges come from in the conductor? There aren't any positive, there's protons and there's electrons, and they even each other out. So there's lots of charges we don't draw on here because the net equals 0. We have the same number of protons, same number of electrons. They cancel each other out. You don't worry about it. So these positive charges really aren't a positive charge per se. It's more along the lines of it's missing the electron. So if we take an electron from here, move it over here, we now have a net negative on this side. We have a net positive on this side, and that's what creates our charges. So that's the idea behind conductors and insulators. Okay. Now, there are a lot of implications from this. A lot that aren't too intuitive. So we're going to go through some examples and look at them. Here we are. Example number 1. All right. So the idea here is a metal sphere of radius A. Check. Got that. Contains a charge plus Q. Okay. So here it means net positive Q. There are probably some negatives in there as well, but when everything cancels out, you get plus Q. And it's surrounded by an uncharged, concentric, metallic, i.e. conductor, shell of inner radius B, and outer radius C, as shown above. Okay? Express all algebraic answers in terms of given quantities in fundamental constants. Okay, so fundamental constants, it means probably K, or K is also equal to 1 over 4 pi epsilon naught. I don't know if I've even mentioned that. Not important yet. We'll get to that later. Determine the induced charge on each of the following. Okay? So you can just think of it as charge due to electric fields on each of the following and explain the reasoning in each case. So the inner surface of the metallic sphere. Okay? Or inner shell. So shell, this is shell. That is sphere. All right, the inner surface. So we want to find the Q total on the inner side. So there's a couple of different ways of looking at this. So if we zoom in on this portion right here, what we have is something like this, and then something like this. So we have an air gap, and then we have a sphere. So this is going to be positives. Now they don't tell us that the inner part is a conductor or not, and it doesn't actually matter. No, they do. Metal sphere. So the inner part's a conductor, which means all the positive charges will be on the outside. And what this is going to do is this is going to attract negative charges. Now the metal shell on the outside surrounded by an uncharged. So there's no net charge on the outer shell. So what we're going to have here is all the positive charge on the inner sphere are going to attract the negative charges on the outer sphere. And then the question is, how? So we're pretty sure it's going to be negative. So the induced charge on the inner shell, pretty sure it's going to be negative. We want to know how much. Now, one thing we really haven't discussed much here is if you go back to, let's say we have a sphere of charges, and we look at what's the, in its insulator uniform charge, we just have a ball of charge. And if we ask, so at some radius r, let's do this guy. We have some radius r like this. What's going to be the charge? So this entire thing is big Q, and we have some smaller part here. What's going to be the electric field at this point? Well, what's going to happen is the electric field is going to get bigger and bigger as we go out to the full distance. And that's because as we go bigger, we have more charge on the inside of what we're measuring. This wouldn't work with a conductor because all the charges would be at the outside. But if this is an insulator, we have all these universally distributed charges. Then if we're like, all right, the electric field at R would equal K, and I'm going to use the nomenclature Q enclosed over R squared. Now the idea is we can ignore the ignore the charges that are not enclosed, i.e. out here. This is pretty much Gauss's law, which I haven't discussed yet. I'll discuss next time. But I'm going to try and do it in a more intuitive way here. Just kind of give you the warm fuzzies. So the idea behind this, on why you can ignore the ones on the outside, is if we look at the electric field right here, everything from the circle is pulling it towards this center right there. But these charges here might be pulling you this direction, while these charges over here are pulling you this direction. And kind of the idea here is if you draw, that's terrible. This area right here, it's has fewer charges, but it's closer to the point we're measuring. And this section over here has more charges. Let's say this is the same angle on both these lines here. they are more charges, but they're farther away. And so the fewer charges but closer, more charges but further, balance each other out exactly, and so they have no effect. This shouldn't be a new concept for you because you saw the exact same thing with gravity. If you had Earth like this and you dug your way and were, boiling or whatnot, or any other environmental issues, you'd be like, well, what's the gravity at some point halfway between the center of the Earth and the surface? Well, you would only use the radius up to that halfway point to find the sphere and find out what's attracting you towards it. Big story here is you can ignore everything on the outside. That's a shell shape in terms of gravity. Same thing goes for charges, right? Big concept. We're going to go with that. Okay. So the idea that you can ignore everything outside of you, we're going to go with another idea here. So we have plus charges on the inside sphere, negative on the outside of the, or inside of the shell, and then there's going to be some pluses out here, but we don't really care about those yet. So another thing I said was the electric field inside a conductor is always 0. So if we look at the electric field at this point right here, electric field, what we can do is we can look at the charges inside of this imaginary sphere at this point, and we know that the electric field has to equal 0 because it's inside a conductor. This is a conducting shell. Metallic shell? Metallic shell. We know the electric field is going to be equal to 0. Well, we know that K, which is a constant, is always going to be K. We have Q enclosed over R squared, which is the radius here. Now we can choose this sphere to be anywhere inside the shell. We're going to choose it just on the other side of the negative charges. So that it's almost at the negative charges, but the negative charges are on the surface, the inner surface of the sphere. But our sphere radius that we're actually measuring is just inside of the conductor. So we're going to say that's kind of sort of R is kind of sort of B. I'm going to say B plus. Pluses are also nicer, but it just means a little bit more. So for the only way for this to work, we know K is positive, we know R is positive. This is going to tell us that Q enclosed has to equal negative, or Q enclosed has to equal 0. We know that Q enclosed includes the positive charges from the sphere. So the negative charges here have to be negative Q. So that's a lot of words to say something that was probably fairly intuitive. And that's that that was terrifying. It looked almost like a little earthquake, but it's just me shaking the screen. So the charges on the inside of the shell are going to be negative Q. Now, let's see. Determine the induced charge on each of the following. Explain your reasoning of the case. So, negative Q. And the way you could explain this would be Gauss's law. We'll explain that later. I just want to get the right answer here. Basically, Q enclosed equals 0. Boom, boom, boom. Yes. Insert. Okay. So one thing to note, though, is that even though the charges added up for all inside the sphere will be the same as this inner shell, will be the same as the sphere, the density of the charges on the inner sphere, so you'll normally see like an area density, which will be a certain small amount of Q for a small amount of area. That will be different from the shell than from the sphere because the shell is bigger, so it'll have a lower density, but it'll have the same number of charges, electrons, if you will. Does that seem reasonable? So the induced charge on the inner shell will be negative Q. And the justification for that will be using Gauss's law, which we'll talk about later. Q enclosed equals 0. The outer surface of the metallic shell. So that's asking here. So we can use the same reasoning then that you can't use the electric field equals 0, but we're looking at the Q enclosed. And the Q enclosed is going to be the only charge we have enclosed is the sphere. So it's going to exactly balance out just like the inner one did. And I'm not going to give as good of a justification for this one. This is more just an idea of, so you have a electrically neutral conducting shell, and the charges are going to migrate as such, with plus Q on the outside, minus Q on the inside. And then when you add up all the Q's, you're just going to have the positive Q's that were from the inner sphere. Plus Q. All right. Determine expressions for the magnitude of the electric field as a function of R. Okay. The distance from the center of the inner sphere in each of the following regions. And then it wants us to, I believe, graph it. Yep, and then it wants us to sketch. Oh, okay. So, we know the electric field inside a conductor is 0. So we're going to go with that. And when we look at it from the outside, all we're going to see from the net charge is the charges that we had from the sphere in the middle. So if we go really far away, it's going to look as if we have charges of plus Q. So the equation we're going to have for the electric field is cyan. I think it's cyan. I should look it up, make sure that's actually the correct color name. I think it's cyan. I feel bad I've been saying it wrong this whole time. So electric field equals K positive Q. It's supposed to be positive Q, not plus Q. Yes. Over R squared. This is the equation that this is Coulomb's law, what we've been talking about from the whole time. And from a great distance, that's what it's going to look like. So the way I'm going to do this is I'm actually going to start by sketching it. I'm going to draw 1 over R squared. Oh, that seems reasonable. And this is K plus Q over R squared, which is the electric field. And then what I'm going to do is it's going to act like that, but then it's going to be 0 inside all the conductors, because the conductors will rearrange the charges within inside the conductor so that the electric field is 0. And so what I'm going to do is a little bit darker blue to make it more serious. So it's going to look like this. And then A to B, there's an air gap. B to C, there is another conductor. Do I have an eraser button? Ooh, eraser. Oh no, I didn't want to erase the whole thing. How tragic. Okay. I'll leave that then. So I'll just X this out. X that out. X that out. And this will be the region. So from R less than A inside a conductor, so 0 electric field. R to B, be KQ over R squared. B to C, 0. And greater than R, we'll have KQ over R squared. Yep. And you can look at that from a Q enclosed perspective too. So in here, the Q enclosed will be plus Q. Q enclosed has mean enclosed charge within our imaginary sphere of radius R. Then if we go for between B and C, we have the charge enclosed is plus Q and minus Q. Add them together to get 0. We go to the end, and we have 2 plus Q's, 1 minus Q, which gives us a net positive Q. And you'll see these problems pop up every now and then. And things to take note would be, what are insulators, what are conductors? A lot of times you'll see that the inner one will be an insulator. And so the whole idea of the electric field inside is 0 does not apply if it's an insulator. As you get bigger, you have more charge enclosed, and you get more of a more electric field. So boom, 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 boom. Yes. So when you see these problems, something like this, especially with all metallic spheres, I would just start by writing the alternating Q's. So you have positive Q in the middle, you're going to have a negative Q, and on the outside of the shell, you're going to have positive Q. And then if you have more spheres, you just keep alternating, have another one, you would write another metallic sphere like this, write negative Q plus Q. And if you have just an insulator with no net charge, there's no charge at all in it, and it's as if it was not there. And if you have an insulator with a net charge on it, then you'd have to do the whole calculations to figure out how much of that shell is actually enclosed. And electron. Okay. So then we got one last part. These are a beast of a problem. We have like on the AP test, about 15 minutes to do a test, to do a problem like this. This is taking me, what, 20, 30 minutes already? Outrageous. Outrageous. You have to go through these pretty quick. This is a beast of a test. I will admit to that. All right. One last problem for this part. An electron of mass ME seems reasonable. Carrying a charge of negative E, also reasonable, is released from rest at a very large distance. So by very large distance, I'm going to say infinity from the spheres. Derive an expression for the speed of the particle at a distance of 10 r from the center of the spheres. Okay, so this is almost like a completely different problem. So I'm going to draw our spheres like this. This is 10r. From the spheres. So I'm going to assume that r is greater than 10r is greater than c. So we can't know that for sure. It is greater than c. So it's outside the sphere. So it says 10r from the center of the spheres. So we don't know if it's outside the spheres or not. But we're going to assume that. So we have an electron over here. This is positively charged. So the electron is going to be drawn this way. So whenever we see something like this, we're thinking about work and energy. And so we have potential energy here being converted to kinetic energy. And the question is, how much kinetic energy? So first thing is, how much potential energy is between these two? Then when we convert that to kinetic energy, how much speed does that translate to? So I'm going to start with I always start these out. Work equals mass times acceleration times distance, which work equals force times distance. This will be a little bit more exact. That is integral f dot dr. And I like to start with the simple and then kind of work my way up to more exact, because one, it just helps me, it's easier for me to memorize things this way instead of just memorizing f dot dr. And another thing is, the problem might be simple enough that you don't need the integral. It might be like, oh, f is constant, distance is known, we'll call that good. So in this case, we know that force equals K Q. I'm just going to call this Q positive, and then Q electron. But they give us a charge at E minus, but I feel more comfortable with Q E for now. So that's what I'm going to go, and I will change it later. Over R squared. So we can do this as K, Q plus, QE, R to the negative 2, dr. And then I'm going to draw the integral symbol right there, because what I did is I basically pulled out the constants. Delicious. And then we're going to go from infinity to 10r. Yeah, that seems reasonable. Yeah, I'm good with that for now. All right. So we'll have K, Q positive, Q electron, R. So negative 2, we'll do plus 1 is negative 1. Then we'll divide by negative 1. I might have had a sign wrong somewhere. Oh well, we'll figure this out. So then we'd have 10r to infinity, which equals, I'm gonna, I did have a sign wrong, not sure why. Oh well, I'll figure it out in a bit. K, Q positive, QE, negative 1, and then we have 1 over 10r minus 1 over infinity. 1 over infinity goes to 0, and we have K, Q, I'll write this now as Q plus, E minus, and then I'm just going to divide by 10r. Not quite sure why I have that negative. Maybe it's because the electron is a negative charge, which would make sense. Negative E, that could be it. Not entirely sure. Either way, I want to have a positive amount of energy because I know that I'm converting potential energy to kinetic, and so it should be moving. And this will equal 1/2 mv squared, mass of electron, and then we have v squared equals 2 q plus e minus over 10 mass of the electron. Oop. Get rid of that number. That becomes 5. So we have arrow speed equals square root of q e minus all over 5 mass of the electron. So one other thing to note, this dot over here is not really a multiplication symbol but a dot product. And the dot product has to do with cosine of theta. There's a cosine of theta in there. But since the electron is moving directly at these spheres, that theta equals 0, so the cosine of 0 is 1. So it could be safely ignored and treated as just a multiplication. And that's why I was able to do that. If it was moving off at a funny angle, that'd be different. So here we got, this is the final velocity of the electron moving in. Make sure that's what they're looking for the speed. Yep, it's speed, not velocity. But we could say velocity by making a little r hat. Negative r hat? Probably negative r hat. At a distance of 10r. And that's, yep, distance of 10r from the conductors. Okay? And that is a free response example for conductors and insulator. Just a second, we'll go over a couple of multiple choice ones as well. Here we have a couple of multiple choice questions. These are quicker to do. You only have about a minute or so to do these problems. It doesn't really make them easier because they're higher risk. They have no partial credit. But there's a 1 in 5 chance that you'll get them right just by guessing. So, and since you only need like maybe a 60 on the test, it's like, maybe. Either way, multiple choice, a lot of stress in my life. All right, all the following statements about an isolated, solid, charged conductor are correct except. Okay, so isolated here I'm assuming what they're going for with isolated is no electric fields. So there's not like some sort of charge out there that's creating an induced charge and moving all the negative charges to one side and positive to the other. So this solid charged conductor, I'm going to say it looks like this, are correct except, okay, all parts of the conductor are at the same potential. We really haven't discussed voltage yet, potential. That's true. I'm just going to leave it at that one. Yes. A quick note on that is I refer to potential as potential energy, and it has to do with what we were talking about earlier with the electric field and electron moving towards and converting potential energy to kinetic energy. So on a slight tangent sidebar, one of the reasons you can justify that electric fields inside a conductor are zero is charges are free to move inside a conductor. So let's say, for example, as a counterexample, that an electric field is not zero within a conductor. So we have a conductor here, and we have an electric field that goes like this. So it's the same as having a positives here and negative charge over here. And so we have a random electron hanging out right here. And so what's going to happen is this electron inside the conductor is going to naturally move over towards the positive. Well, what's going to happen then is this negative electron is basically going to meet up with one of the positive, not positron, but pair up with a proton to basically cancel it out. And what's going to happen is all the charges inside can move, and if there is an electric field, they will move, and eventually they'll all keep moving until they quit moving. If you had an electric field within inside a conductor, there'd be this perpetual motion of things zooming around. And since since they're zooming around to basically go to where the least amount of energy is, i.e. this electron moving towards these positrons, these positive charges, they're moving to minimize the electric field. And so what's going to happen is all the charges that can move will move to meet the minimum energy. And once everything is settled, which is not instantaneously, but pretty darn quick, then there will be no electric field within the conductor. Because if there was an electric field, the electrons would just move to minimize it, which would then be zero. And that's one of the ways you can justify why there is no electric field within a conductor, is because the electrons would move to get rid of it pretty much instantly. And that also kind of ties into potential energy, which we'll cover when we talk about potential. All correct except, so we're looking for the one that is wrong. All excess charges resides on the outer surface. That's true. The charges want to get as far away from each other, so not just for a sphere, but any shape. I don't think it's true for things that are hollow, which is why they say solid. Not sure about that. I'll have to check that out. But the idea here is they're all going to be on the outer surface because they want to get as far away from each other as possible. Now, if you have an irregular shape, they won't all have the same surface charge density, but they'll all be on the surface. The net charge enclosed by any surface lying entirely within the conductor must equal zero. Yes, so these two are saying the same thing, which is why there can only be one wrong here. So if you have two things that say the same, you know that they can't be options. Did they follow that? I hope you followed that. Yeah. You got it. All excess. Did you? So if there can only be one wrong answer here, and you have two answers that are the same, they can't both be wrong. Therefore, they have to both be correct. Trust me on this one. The net charge enclosed by any surface lying entirely within the conductor must equal 0. So we know all the charges are on the outside, net charges. And therefore, when you have a chunk of the interior, that chunk of the interior will have no net charges on it, no excess on it. So that is also true. Electric field just outside the conductor is directed parallel to the surface. That's just false. So all electric field lines leaving a conductor are always perpendicular. One way to kind of remember that, not like a mnemonic, is when you see the picture of a charged particle with electric field, they're always going out like this, and these are all perpendicular. Turns out it's true for any shape of a charged conductor as well. But this says parallel, like this for electric lines, not true. So that one's false. Electric field intensity inside the conductor is 0. So yes, the electric field inside is 0. So this question, 5, is D. Whew. Very difficult, very challenging. All right, 15, last one. Hold on, like 2 minutes, maybe 4. I'm slow in talking with these. A negatively charged conductor attracts a second object. Okay. Negatively charged conductor has negative charges on the outside. Okay. I probably wouldn't I might draw this. If I was taking the test, I might actually draw this out real quick. Just a blob and some negatives. The second object could be which of the following? Okay. A conductor with positive net charge. Yep. And I draw these evenly, but if it's attracted, there'd actually be more positives on this side. There might actually, depending on how many excess there are, there may be some positives on the other side as well. But there would be more positives on this side. Yes, they would be attracted. A conductor with positive net charge, a conductor with 0 net charge. Yes, that one would also be attracted because you would have an induced charge. So, in case you don't see where this one's going, so negative, you have net charge of 0. And so when you add them all up, you get 0. So what happens here then is these negatives attract the positives. I say the positive, but really what it's doing is pushing the electrons away. But for all intents and purposes, you can pretend that there's positive charges and negative charges. Which they're kind of... Well, let's go with that fiction for now. Version of reality. We'll go with that. Version of reality. So we have the positive charges here, negative charges here. The net is negative, but it's a conductor, so the positives want to move as close as they can to the negative charges on the other object, and the negative charges want to move as far away as possible. And so what happens is force equals QE plus QB cross B, which is 0. And so this is KQ over R squared. So it's the R squared that matters. This distance is smaller, R small, R big. And since you have a small radius here, smaller, you're going to feel a greater force from, with a greater force of attraction from the positive charges because they've already been pulled close, than a repulsive force from the negatives, which are slightly further away. And therefore, the net force would be positive. So it would be an attraction, a conductor with net charge. So true, true. Maybe I should circle for true. I don't know. An insulator with 0 net charge. Okay, so you generally think of insulators as homogeneous, as even, and everything is the same. That's not necessarily true. You could just have an insulator which looks like this, just a block. You have a positive insulator and a negative insulator, and you just took it and you just put them together as a block. And then if you put this insulator over here, it would act the same way as this conductor, where the positives are physically closer than the negatives. So there is no guarantee with this insulator that it's homogeneous. So if you have a homogeneous insulator, where positive and negatives are all mixed together, then you wouldn't feel any sort of attraction, because the negatives and positives all offset each other. There is no guarantee that an insulator would be homogeneous and the same all over. So it is, which the second object could be. So it could be possible. It seems unlikely. You'd go to a lot of effort to make a special insulator that's not the same on both sides, not the same throughout, but it's possible. And that's why 1, 2, or 3. And that's why E would be the answer for that. So this covers what I want to go over for insulators. Next time we'll go over Gauss's law, which will explain a lot of what I kind of took for granted here. But these are the kind of questions you're going to see pop up. And there always seems to be sort of exceptions that you can think of. So a lot of the game here, the tricks here, the challenge is to visualize conductors and insulators, and then how the two will interact with each other. All right, appreciate the patience. I know these conductors and insulators, it sounds simple, but man, they can get really complicated with some of the questions. Thank you much. See you next time for Gauss's law.